Chapter 8. The 19th Century. The French Revolution and the Napoleonic period created extremely favorable conditions for the further growth of mathematics. The way was open for the Industrial Revolution on the continent of Europe. This stimulated the cultivation of the physical sciences and created new social classes with a new outlook on life, interested in science and in technical education. The democratic ideas invaded academic life. Criticism rose against antiquated forms of thinking. Schools and universities had to be reformed and rejuvenated. The new and turbulent mathematical productivity was not primarily due to the technical problems raised by the new industries. England, the heart of the Industrial Revolution, remained mathematically sterile for several decades. Mathematics progressed most healthily in France and somewhat later in Germany, countries in which the ideological break with the past was most sharply felt and where sweeping changes were made, or had to be made, to prepare the ground for the new capitalist economic and political structure. The new mathematical research gradually emancipated itself from the ancient tendency to see in mechanics and astronomy the final goal of the exact sciences. The pursuit of science as a whole became even more detached from the demands of economic life or of warfare. The specialists developed, interested in science for its own sake. The connection with practice was never entirely broken, but it often became obscured. A division between pure and applied mathematics accompanied the growth of specialization. Mathematicians of the 19th century were no longer at royal courts or in the salons of the aristocracy. Their chief occupation was no longer membership in a learned academy. They were usually employed by universities or technical schools, and were teachers as well as investigators. The Bernoulli, Lagrange, and Laplace had done occasional teaching. Now the teaching responsibility increased. Mathematics professors became educators and examiners of the youth. The internationalism of previous centuries tended to be undermined by the growing relationship between the scientists of each nation, though international exchange of opinion did remain. Scientific Latin was gradually replaced by the national languages. Mathematicians began to work in specialized fields. And while Leibniz, Euler, and D'Alembert can be described as mathematicians, as geometers in the 18th century meaning of the word, we think of Cauchy as an analyst, of Cayley as an algebraist, of Steiner as a geometer, even a pure geometer, and of Cantor as a pioneer in point-set theory, theory of aggregates. The time was ripe for mathematical physicists, followed by men learned in mathematical statistics or mathematical logic. Specialization was only broken on the highest level of genius, and it was from the works of a Gauss, a Riemann, a Klein, a Poincare that 19th century mathematics received its most powerful impetus. On the dividing line between 18th and 19th century mathematics towers the majestic figure of Carl Friedrich Gauss. He was born in the German city of Brunswick, the son of a day laborer. The Duke of Brunswick recognized in young Gauss an infant prodigy and took charge of his education. The young genius studied from 1795 to 1798 at Göttingen, and in 1799 obtained his doctor's degree at Helmstadt. From 1807 until his death in 1855, he worked quietly and undisturbed as the director of the Astronomical Observatory and professor at the university of his alma mater. His comparative isolation, his grasp of applied as well as pure mathematics, his preoccupation with astronomy, and his frequent use of Latin have the touch of the 18th century, but his work breathes the spirit of a new period. He stood, with his contemporaries, Kant, Goethe, Beethoven, and Hegel, on the sidelines of a great political struggle raging in other countries, but expressed in his own field the new ideas of his age in a most powerful way. Gauss's diaries show that in his 17th year he had already begun to make startling discoveries. In 1795, for instance, he discovered independently of Euler the law of quadratic reciprocity in number theory. Some of his early discoveries were published in his Helmstadt dissertation of 1799 and in the impressive Disquisitiones Arithmeticae of 1801. The dissertation gave the first rigorous proof of the so-called fundamental theorem of algebra, which states that every algebraic equation with real coefficients has at least one root, and whence has a number of roots equal to its degree. The theorem goes back to Albert Girard, the editor of Stevin's works. D'Alembert had tried to give a proof in 1746. Gauss loved this theorem, and later gave two more demonstrations. returning in the fourth to his first proof. The third demonstration used complex integrals and showed Gauss's early mastery of the theory of complex numbers. The Disquisitiones Arithmeticae collected all the masterful work in number theory of Gauss's predecessors, and enriched it to such an extent that the beginning of modern number theory is sometimes dated from the publication of this book. Its core is the theory of quadratic congruences, forms, and residues. It culminates in the law of quadratic residues, for which Gauss gave the first complete proof. Gauss was as fascinated by this theorem as by the fundamental theorem of algebra, and later published 5 more demonstrations. One more was found after his death among his papers. The Disquisitions also contain Gauss's studies on the division of the circle. In other words, on the roots of the equation x raised to the power of n equals 1. They led to the remarkable theorem that the sides of the regular polygon of 17 sides, or more generally of n sides where n is equal to 2 to the power of k plus 1, and n is prime and k is 0, 1, 2, 3, and so on, can be constructed with compass and ruler alone, a striking extension of the Greek type of geometry. Gauss's interest in astronomy was aroused when, on the first day of the new century, Piazzi in Palermo discovered the first planetoid, which was given the name of Ceres, since only a few observations of the new planetoid could be made. The problem arose to compute the orbit of a planet from a small number of observations. Gauss solved the problem completely. It leads to an equation of degree 8 when in 1802, Pallas, another planetoid, was discovered. Gauss began to take an interest in the secular perturbations of planets. This led to the theory of the motion of the heavenly bodies, to his paper on the attraction of general ellipsoids, to his work on mechanical quadrature, and to his study of secular perturbations. To this period belongs also Gauss's paper on the hypergeometric series, which allows a discussion of a large number of functions from a single point of view. It is the first systematic investigation into the convergence of a series. After 1820, Gauss began to be actively interested in geodesy. Here, he combined extensive applied work in triangulation with his theoretical research. One of the results was his exposition of the method of least squares, already the subject of investigation by Legendre and Laplace. Perhaps the most important contribution of this period in Gauss's life was the surface theory of the Disquisitions Generales circa superficies curvae, which approached its subject in a way strikingly different from that of Monge. Here again practical considerations, now, in the field of higher geodesy, were intimately connected with subtle theoretical analysis. In this publication appeared the so-called intrinsic geometry of a surface, in which curvilinear coordinates are used to express the linear element in a quadratic differential form. There was also a climax, the Theorema egregium, which states that the total curvature of the surface depends only on certain functions and their derivatives, and thus is a bending invariant. But Gauss did not neglect his first love, the queen of mathematics, even in this period of concentrated activity on problems of geodesy, for in 1825 and 1831 appeared his work on biquadratic residues. It was a continuation of his theory of quadratic residues in the Disquisitiones Arithmeticae, but a continuation with the aid of a new method, the theory of complex numbers. The treatise of 1831 did not only give an algebra of complex numbers, but also an arithmetic. A new prime number theory appeared, in which 3 remains prime, but 5, which equals 1 plus 2 times the square root of -1, multiplied by 1 minus 2 times the square root of -1, is no longer a prime. This new complex number theory clarified many dark points in arithmetic so that the law of quadratic reciprocity became simpler than in real numbers. In this paper, Gauss dispelled forever the mystery which still surrounded complex numbers by his representation of them by points in a plane. A statue in Göttingen represents Gauss and his younger colleague Wilhelm Weber in the process of inventing the electric telegraph. This happened in 1833 and 1834, at a time when Gauss's attention began to turn to physics. In this period he did much experimental work on terrestrial magnetism. But he also found time for a theoretical contribution of the first importance, his general propositions on the theory of forces acting inversely proportional to the square of the distance. This was the beginning of potential theory as a separate branch of mathematics, and it led to certain minimal principles concerning space integrals, in which we recognize Dirichlet's principle. For Gauss, the existence of a minimum was evident. This later became a much debated question, which was finally solved by Hilbert. Gauss remained active until his death in 1855. In his later years, he concentrated more and more on applied mathematics. His publications, however, do not give an adequate picture of his full greatness. The appearance of his diaries and of some of his letters has shown that he kept some of his most penetrating thoughts to himself. We now know that Gauss, as early as 1800, had discovered elliptic functions and around 1816 was in possession of non-Euclidean geometry. He never published anything on these subjects. Indeed, only in some letters to friends did he disclose his critical position toward attempts to prove Euclid's parallel axiom. Gauss seems to have been unwilling to venture publicly into any controversial subject. In letters he wrote about the wasps who would then fly around his ears and of the shouts of the Boeotians that would be heard if his secrets were not kept. For himself, Gauss doubted the validity of the accepted Kantian doctrine that space conception is Euclidean a priori. For him, the real geometry of space was a physical fact to be discovered by experiment. In his History of Mathematics of the 19th century, Felix Klein has invited comparison between Gauss and the 25-year-older French mathematician, Adrien-Marie Legendre. It is perhaps not entirely fair to compare Gauss with any mathematician except the very greatest. But this particular comparison shows how Gauss's ideas were in the air, since Legendre in his own independent way worked on most subjects which occupied Gauss. Legendre taught from 1775 to 1780 at the military school in Paris, and later filled several different government positions, such as professor at the École Normale, examiner at the École Polytechnique, and geodetic surveyor. Like Gauss, he did fundamental work on number theory in his work, Essay on the Theory of Numbers, in which he gave a formulation of the law of quadratic reciprocity. He also did important work on geodesy and on theoretical astronomy. Was an assiduous computer of tables like Gauss, formulated in 1806 the method of least squares, and studied the attraction of ellipsoids, even those which are not surfaces of revolution. Here he introduced the Legendre functions. He also shared Gauss's interest in elliptic and Eulerian integrals, as well as in the foundations and methods of Euclidean geometry. Although Gauss penetrated deeper into the nature of all these different fields of mathematics, Legendre produced works of outstanding importance. His comprehensive textbooks were for a long time authoritative, especially his exercises in integral calculus and his treatise on elliptic functions and Eulerian integrals, which is still a standard work. In his Elements of Geometry he broke with the Platonic ideals of Euclid, and presented a textbook of elementary geometry based on the requirements of modern education. This book passed through many editions and was translated into several languages. It has had a lasting influence. The beginnings of the new period in the history of French mathematics may be dated perhaps from the establishment of military schools and academies, which took place during the latter part of the 18th century. These schools, of which some were also founded outside of France, such as in Turin and Woolwich, paid considerable attention to the teaching of mathematics as a part of the training of military engineers. Lagrange started his career at the Turin School of Artillery. Legendre and Laplace taught at the military school in Paris, Monge at Mézières. Carnot was a captain of engineers. Napoleon's interest in mathematics dates back to his student days at the military academies of Brienne and Paris. During the invasion of France by the royalist armies, the need for more centralized instruction in military engineering became apparent. This led to the foundation of the École Polytechnique of Paris in 1794, a school which soon developed into a leading institution for the study of general engineering and eventually became the model of all engineering and military schools of the early 19th century, including West Point in the United States. Instruction in theoretical and applied mathematics was an integral part of the curriculum. Emphasis was laid upon research as well as upon teaching. The best scientists of France were induced to lend their support to the school. Many great French mathematicians were students, professors, or examiners at the École Polytechnique. The instruction at this institution, as well as at other technical schools, required a new type of textbook. The learned treatises for the initiated, which were so typical of Euler's period, had to be supplemented by college handbooks. Some of the best textbooks of the early 19th century were prepared for the instruction at the École Polytechnique or similar institutions. Their influence can be traced in our present-day texts. A good example of such a handbook is the Treatise on Differential and Integral Calculus, written by Sylvestre François Lacroix, from which whole generations have learned calculus. We have already mentioned Legendre's books. A further example is Monge's textbook of descriptive geometry, which still is followed by many present-day books on this subject. Gaspard Monge, the director of the École Polytechnique, was the scientific leader of the group of mathematicians who were connected with this institute. He had started his career as an instructor at the Military Academy of Mezieres from 1768 to 1789, where his lectures on fortification gave him an opportunity to develop descriptive geometry as a special branch of geometry. He published his lectures in the work Descriptive Geometry. At Mezieres he also began to apply calculus to space curves and surfaces, and his papers on this subject were later published in the work Application of Analysis to Geometry, the first book on differential geometry, though not yet in the form which is customary at present. Monge was one of the first modern mathematicians whom we recognize as a specialist, a geometer. Even his treatment of partial differential equations has a distinctly geometrical touch. Through Monge's influence, geometry began to flourish at the École Polytechnique. In Monge's descriptive geometry lay the nucleus of projective geometry, and his mastery of algebraic and analytical methods in their application to curves and surfaces contributed greatly to analytical and differential geometry. Jean Hachette and Jean-Baptiste Biot developed the analytical geometry of conics and quadrics. In Biot's essay on analytical geometry, we begin at last to recognize our present textbooks of analytic geometry. Monge's pupil, Charles Dupin, as a young naval engineer in Napoleonic days, applied his teacher's methods to the theory of surfaces, where he found the asymptotic and conjugate lines. Dupin became a professor of geometry in Paris, and during his long life gained prominence as a politician and industrial promoter as well. The indicatrix of Dupin and the cyclides of Dupin remind us of the early interests of this man, whose developments in geometry and applications of geometry contain a great number of interesting results. The most original Monge pupil was Victor Poncelet. He had an opportunity to reflect on his teacher's methods during 1813, when he lived an isolated existence as a war prisoner in Russia after the defeat of Napoleon's Grande Armée. Poncelet was attracted by the purely synthetic side of Monge's geometry, and thus was led to a mode of thinking already suggested 2 centuries before by Desargues. Poncelet became the founder of projective geometry. Poncelet's treatise on the projective properties of figures appeared in 1822. This heavy volume contains all the essential concepts underlying the new form of geometry, such as cross ratio, perspectivity, projectivity, involution, and even the circular points at infinity. Poncelet knew that the foci of a conic can be considered as the intersections of the tangents at the conic through these circular points. The treatise also contains the theory of the polygons inscribed in one conic and circumscribed to another one, known as the closure problem of Poncelet, although this book was the first full treatise on projective geometry. During the next decades, this geometry reached that degree of perfection which made it a classical example of a well-integrated mathematical structure. Monge, although a man of strict democratic principles, stayed loyal to Napoleon, in whom he saw the executor of the ideals of the Revolution. In 1815, when the Bourbons returned, Monge lost his position, and soon afterward died. The École Polytechnique, however, continued to flourish in Monge's spirit. The very nature of the instruction made it difficult to separate pure and applied mathematics. Mechanics received full attention, and mathematical physics began at last to be emancipated from the catoptrics and the dioptrics of the ancients. Etienne Malus discovered the polarization of light, and Augustin Fresnel re-established Huygens' undulatory theory of light. André-Marie Ampère, who had done distinguished work on partial differential equations, became after 1820 the great pioneer in electromagnetism. These investigators brought many direct and indirect benefits to mathematics. One example is Dupin's improvement of Malus' geometry of light rays, which helped to modernize geometrical optics and also contributed to the geometry of line congruences. Lagrange's analytical mechanics was faithfully studied, and its methods tested and applied. Statics appealed to Monge and his pupils because of its geometrical possibilities. And several textbooks on statics appeared in the course of the years, including one by Monge himself. The geometrical element in statics was brought out in full by Louis Poinsot, for many years a member of the French Superior Board of Public Instruction. His Elements of Statics and New Theory of the Rotation of Bodies added to the conception of force that of torque, represented Euler's theory of moments of inertia by means of the ellipsoid of inertia, and analyzed the motion of this ellipsoid when the rigid body moves in space or turns about a fixed point. Poncelet and Coriolis gave a geometrical touch to Lagrange's analytical mechanics. Both men, as well as Poinsot, stressed the application of mechanics to the theory of simple machines. The acceleration of Coriolis, which appears when a body moves in an accelerated system, is an example of such a geometrical interpretation of Lagrange results. The most outstanding mathematicians connected with the early years of the École Polytechnique were, apart from Lagrange and Monge, Simeon Poisson, Joseph Fourier, and Augustin Cauchy. All three were deeply interested in the application of mathematics to mechanics and physics, and all three were led by this interest to discoveries in pure mathematics. Poisson's productivity is indicated by the frequency in which his name occurs in our textbooks, Poisson's brackets in differential equations, Poisson's constant in elasticity, Poisson's integral, and Poisson's equation in potential theory. This Poisson equation, represented by the mathematical expression Laplacian of W equals 4 times pi times p, was the result of Poisson's discovery that Laplace's equation, represented by the mathematical expression Laplacian of W equals 0, only holds outside of the masses. Its exact proof for masses of variable density was not given until Gauss gave it in his general propositions. Poisson's treatise on mechanics was written in the spirit of Lagrange and Laplace, but contained many innovations, such as the explicit use of impulse coordinates, which later inspired the work of Hamilton and Jacobi. His book of 1837 contains Poisson's law in the theory of probabilities, originally derived as an approximation to the binomial law of Bernoulli for the case of small probabilities, but now recognized as a fundamental law in problems of radiation, traffic, and distribution in general. Fourier is primarily remembered as the author of the analytical theory of heat. This is the mathematical theory of heat conduction and, therefore, is essentially the study of the equation Laplacian of U equals k times the partial derivative of U with respect to t. By virtue of the generality of its method, this book became the source of all modern methods in mathematical physics, involving the integration of partial differential equations under given boundary conditions. This method is the use of trigonometric series, which had been the cause of discussion between Euler, D'Alembert, and Daniel Bernoulli. Fourier made the situation perfectly clear. He established the fact that an arbitrary function, meaning a function capable of being represented by an arc of a continuous curve or by a succession of such arcs, could be represented by a trigonometric series of the form, the sum of a sub n times cosine of n times, a times tas b sub n times a times, sin m times a times, x from equals 0 to infinity. Despite Euler's and Bernoulli's observations, the idea was so new and startling at the time of Fourier's investigations that it is said that, when he stated his ideas in 1807 for the first time, he met with the vigorous opposition of no one other than Lagrange himself. The Fourier series now became a well-established instrument of operation in the theory of partial differential equations with given boundary conditions. It also received attention on its own merits. Its manipulation by Fourier fully opened the question of what to understand by a function. This was one of the reasons why 19th century mathematicians found it necessary to look closer into questions concerning rigor of mathematical proof and the foundation of mathematical conceptions in general. This task, in the specific case of Fourier series, was undertaken by Dirichlet and Riemann. Cauchy's many contributions to the theory of light and to mechanics have been overshadowed by his success in analysis. However, it's important to remember that, along with Navier, he is one of the founders of the mathematical theory of elasticity. His main glory is the theory of functions of a complex variable, and his insistence on rigor in analysis. functions of a complex variable had already been constructed before, notably by D'Alembert, who in a paper on the resistance of fluids in 1752 had obtained what we now call the Cauchy-Riemann equations. In Cauchy's hands, complex function theory was transformed from a tool useful in hydrodynamics and aerodynamics into a new and independent field of mathematical research. Cauchy's investigations on this subject appeared in constant succession after 1814. One of the most important of his papers is the memoir on definite integrals taken between imaginary limits from 1825. In this paper appeared Cauchy's integral theorem with residues. The theorem that every regular function can be expanded around each point in a series convergent in a circle passing through the singular point nearest to that point was published in 1831, the same year in which Gauss published his arithmetical theory of complex numbers. Lorentz' extension of Cauchy's theorem on series was published in 1843, when it was also in the possession of Weierstrass. These facts show that Cauchy's theory did not have to cope with professional resistance. The theory of complex functions was fully accepted from its very beginning. Cauchy, along with his contemporaries Gauss, Abel, and Bolzano, belongs to the pioneers of the new insistence on rigor in mathematics. The 18th century had been essentially a period of experimentation, in which results came pouring in with luxurious abundance. The mathematicians of this age had not paid too much attention to the foundation of their work. It is said that D'Alembert's approach was go forward, and faith will come to you, when they worried about rigor. As Euler and Lagrange occasionally did, their arguments were not always convincing. The time had now arrived for a close concentration on the meaning of the results. What was a function of a real variable, which showed such different behavior in the case of a Fourier series and in the case of a power series? What was its relation to the entirely different function of a complex variable? These questions brought all the unsolved problems about the foundation of the calculus and the existence of the potentially and the actually infinite again into the foreground of mathematical thinking. What Eudoxus had done in the period after the fall of Athenian democracy, Cauchy and his meticulous contemporaries began to accomplish in the period of expanding industrialism. This difference of social setting produced different results. And where Eudoxus' success had the tendency to stifle productivity, the success of the modern reformers stimulated mathematical productivity to a high degree. Cauchy and Gauss were followed by Weierstrass and Cantor. Cauchy gave the foundation of the calculus as we now generally accept it in our textbooks. It can be found in his Cours d'analyse from 1821 and Résumé de leçons données à l'École Royale Polytechnique, Royale Polytechnique, Volume I from 1823. So, Cauchy used D'Alembert's limit concept to define the derivative of a function and establish it on a firmer foundation than his predecessors had been able to do. Starting with the definition of a limit, Cauchy gave examples such as the limit of sin x divided by x for x approaching 0. Then he defined an infinitely small variable as a variable number which has 0 for its limit, and then postulated that delta y and delta x are infinitely small quantities. He then wrote the change in y over the change in x equals the function at x plus an increment minus the function at x divided by the increment, and called the limit as the increment approaches 0 the derived function. He placed the increment as an infinitely small quantity, and h a finite quantity. Cauchy used both Lagrange notation and many of his contributions to real function theory without making any concession to Lagrange's algebraic foundation. The mean value theorem and the remainder of the Taylor series were accepted as Lagrange had derived them, but series were now discussed with due attention to their convergence. Several convergence proofs in the theory of infinite series are named after Cauchy. There are definite steps in his books toward that arithmetization of analysis, which later became the core of Weierstrass's investigations. Cauchy also gave the first existence proof for the solution of a differential equation and of a system of such equations in 1836. In this way, Cauchy offered at last a beginning of an answer to that series of problems and paradoxes which had haunted mathematics since the days of Zeno, and he did this not by denying or ignoring them, but by creating a mathematical technique in which it was possible to do them justice. Cauchy, like his contemporary Balzac, with whom he shared a capacity for an infinite amount of work, was a legitimist and a royalist. Both men had such a deep understanding of values that despite their reactionary ideals, much of their work has retained its fundamental place. Cauchy abandoned his chair at the École Polytechnique after the Revolution of 1830 and spent some years at Turin and Prague. He returned to Paris in 1838. After 1848 he was allowed to stay and teach without having to take the oath of allegiance to the new government. His productivity was so enormous that the French Academy had to restrict the size of all papers sent to the Comtes Rendus in order to cope with Cauchy's output. It is told that he disturbed Laplace so greatly when he read to the French Academy his first paper on the convergence of series that the great man went back home to test the series in his Mécanique Céleste. He found, it seems that no great errors had been committed. This Paris milieu, with its intense mathematical activity, produced, around 1830, a genius of the first order who, comet-like, disappeared as suddenly as he had appeared. Évariste de Galois, the son of a small-town mayor near Paris, was twice refused admission to the École Polytechnique and succeeded at last in entering the École Normale, only to be dismissed. He tried to make a living by tutoring mathematics, maintaining at the same time an uneasy balance between his ardent love for science and for democracy. Galois participated as a Republican in the Revolution of 1830, spent some months in prison, and was soon afterward killed in a duel at the age of 21. Two of the papers he sent for publication got lost on the editor's desk. Some others were published long after his death. On the eve of the duel, he wrote to a friend a summary of his discoveries in the theory of equations. This document, in which he asked his friend to submit his discoveries to the leading mathematicians, ended with the words, "You will publicly ask Jacobi or Gauss to give their opinion not on the truth, but on the importance of the theorems. After this, there will be, I hope, some people who will find it to their advantage to decipher all this mess." This mess contained no less than the theory of groups, the key to modern algebra and to modern geometry. The ideas had already been anticipated to a certain extent by Lagrange and the Italian Ruffini. But Galois had the conception of a complete theory of groups. He expressed the fundamental properties of the transformation group belonging to the roots of an algebraic equation and showed that the field of rationality of these roots was determined by the group. Galois pointed out the central position taken by invariant subgroups. Ancient problems such as the trisection of the angle, the duplication of the cube, the solution of the cubic and biquadratic equation, as well as the solution of an algebraic equation of any degree, found their natural place in the theory of Galois. Galois' letter, as far as we know, was never submitted to Gauss or Jacobi. It never reached a mathematical public until Liouville published most of Galois' papers in his Journal de Mathématiques of 1846. At which period Cauchy had already begun to publish on group theory, 1844-46. It was only then that some mathematicians began to be interested in Galois theories. Full understanding of Galois' importance came only through Camille Jordan's treatise on substitutions 1870, and the subsequent publications by Klein and Lie. Now Galois' unifying principle has been recognized as one of the outstanding achievements of 19th century mathematics. Galois also had ideas on the integrals of algebraic functions of one variable, on what we now call abelian integrals. This brings his manner of thinking closer to that of Riemann. We may speculate on the possibility that if Galois had lived, modern mathematics might have received its deepest inspiration from Paris and the school of Lagrange rather than from Göttingen and the school of Gauss. Another young genius appeared in the 1820s. Niels Henrik Abel, the son of a Norwegian country minister. Abel's short life was almost as tragic as that of Galois. As a student in Christiania, he thought for a while that he had solved the equation of degree 5, but he corrected himself in a pamphlet published in 1824. This was the famous paper in which Abel proved the impossibility of solving the general quintic equation by means of radicals, a problem which had puzzled mathematicians from the time of Bombelli and Witt. Abel now obtained a stipend which enabled him to travel to Berlin, Italy, and France. But tortured by poverty most of his life and unable to get a position worthy of his talents, Abel established few personal mathematical contacts and died in 1829, soon after his return to his native land, at a moment when his greatness began to be recognized by Legendre, Jacobi, and Gauss. In this period of travel, Abel wrote several papers which contain his work on the convergence of series, on abelian integrals, and on elliptic functions. Abel's theorems in the theory of infinite series show that he was able to establish this theory on a reliable foundation. Can you imagine anything more horrible than to claim that 0 equals 1 minus 2 plus 3 minus 4, and so on, n being a positive integer? He wrote to a friend, and he continued, "There is in mathematics hardly a single infinite series of which the sum is determined in a rigorous way." Letter to Holmboe, 1826. Abel's investigations on elliptic functions were conducted in a short but exciting competition with Jacobi. Gauss in his private notes had already found that the inversion of elliptic integrals leads to single-valued, doubly periodic functions, but he never published his ideas. Legend, who had spent so much effort on elliptic integrals, had missed this point entirely and was deeply impressed when, as an old man, he read Abel's discoveries. Abel had the good luck to find a new periodical eager to print his papers. The first volume of the Journal for Pure and Applied Mathematics, edited by Krell, contained no less than 5 of Abel's papers. In the second volume, in 1827, appeared the first part of his research on elliptic functions, with which the theory of doubly periodic functions begins. August Leopold Krell, architect and planner of the first railroad in Prussia, is still known through his calculation tables, and as the founder of the still existing Journal for Pure and Applied Mathematics in 1826, one of the first purely mathematical journals, where Krell encouraged young mathematicians such as Abel and Steiner. It took its name from Gergonne's journal. We speak of Abel's integral equation, and of Abel's theorem on the sum of integrals of algebraic functions, which leads to abelian functions. Commutative groups are called abelian groups, which indicates how close Galois ideas were related to those of Abel. In 1829, the year in which Abel died, Carl Gustav Jacob Jacobi published his new foundations of the theory of elliptic functions. The author was a young professor at the University of Königsberg. He was the son of a Berlin banker and a member of a distinguished family. His brother Moritz in St. Petersburg was one of the earliest Russian scientists who experimented in electricity. After studying in Berlin, Jacobi taught at Königsberg from 1826 to 1843. He then spent some time in Italy trying to regain his health and ended his career as a professor at the University of Berlin, dying in 1851 at the age of 46. He was a witty and liberal thinker, an inspiring teacher, and a scientist whose enormous energy and clarity of thought left few branches of mathematics untouched. Jacobi based his theory of elliptic functions on 4 functions, defined by infinite series and called theta functions. The doubly periodic functions sin u, cnu, and dnu are quotients of theta functions. They satisfy certain identities and addition theorems very much like the sine and cosine functions of ordinary trigonometry. The addition theorems of elliptic functions can also be considered as special applications of Abel's theorem on the sum of integrals of algebraic functions. The question now arose whether hyperelliptic integrals could be inverted in the way elliptic integrals had been inverted to yield elliptic functions. The solution was found by Jacobi in 1832 when he published his result that the inversion could be performed with functions of more than one variable. Thus was born the theory of abelian functions of multiple variables, which became an important branch of 19th century mathematics. Sylvester has given the name Jacobian to the functional determinant in order to pay respect to Jacobid's work on algebra and elimination theory. The best known of Jacobi's papers on this subject is his On the Formation and Properties of Determinants from 1841, which made the theory of determinants the common property of mathematicians. The idea of the determinant is much older. It dates back essentially to Leibniz in 1693, the Swiss mathematician Gabriel Kramer in 1750, and Lagrange in 1773. The name is due to Cauchy in 1812. Why? Mikami has pointed out that the Japanese mathematician Sekikowa had the idea of a determinant sometime before 1683. We are here reminded of the matrix methods developed by the Chinese mathematicians of the Sung period. The best approach to Jacobi is perhaps through his beautiful lectures on dynamics, published in 1866 after lecture notes from 1842-43. They are written in the tradition of the French school of Lagrange and Poisson, but have a wealth of new ideas. Here we find Jacobi's investigations on partial differential equations of the first order and their application to the differential equations of dynamics. An interesting chapter of the lectures on dynamics is the determination of the geodesics on an ellipsoid. The problem leads to a relation between two abelian integrals. Jacobi's lectures on dynamics lead us to another mathematician whose name is often linked with that of Jacobi. William Rowan Hamilton, not to be confused with his contemporary, William Hamilton, the Edinburgh philosopher. He lived his whole life in Dublin, where he was born of Irish parents. He entered Trinity College, became Royal Astronomer of Ireland in 1827 at the age of 21, and held this position until his death in 1865. As a boy, he learned continental mathematics, still a novelty in the United Kingdom, by studying Clairaut and Laplace, and showed his mastery of the novel methods in his extremely original work on optics and dynamics. His theory of optical rays in 1824 was more than merely a differential geometry of line congruences. It was also a theory of optical instruments, and allowed Hamilton to predict the conical refractions in biaxial crystals. In this paper appeared his characteristic function, which became the guiding idea of the general method in dynamics, published in 1834-35. Hamilton's idea was to derive both optics and dynamics from one general principle. Rodart, in his defense of Maupertuis, had already shown how the stationary value of the action integral could serve this purpose. Hamilton, in accordance with this suggestion, made optics and dynamics two aspects of the calculus of variations. He asked for the stationary value of a certain integral and considered it as a function of its limits. This was the characteristic or principal function, which satisfied two partial differential equations. One of these partial differential equations was specially selected by Jacobi for his lectures on dynamics and is now known as the Hamilton-Jacobi equation. This has obscured the importance of Hamilton's characteristic function, which had the central place in his theory as a means of unifying mechanics and mathematical physics. It was rediscovered by the Leipzig astronomer Heinrich Bruns in 1895, in the case of geometrical optics, and as Akinel has shown its use in the theory of optical instruments. The part of Hamilton's work on dynamics which has passed into the general body of mathematics is, in the first place, the canonical form in which he wrote the equations of dynamics. Canonical form and the Hamilton-Jacobi differential equation have enabled Lie to establish the relation between dynamics and contact transformations. Another idea of Hamilton, since equally accepted, was the derivation of the laws of physics and mechanics from the variation of an integral. Modern relativity, as well as quantum mechanics, has based itself on Hamiltonian functions as its underlying principle. The year 1843 was a turning point in Hamilton's life. In that year, he found the quaternions, to the study of which he devoted the latter part of his life. We shall discuss this discovery later. Peter Lejeune Dirichlet was closely associated with Gauss and Jacobi, as well as with the French mathematicians. He lived from 1822 to 1827 as a private tutor and met Fourier, whose book he studied. He also became familiar with Gauss's Disquisitions Arithmeticae. Later, he taught at the University of Breslau, and in 1855 succeeded Gauss at Göttingen. His personal acquaintance with French as well as German mathematics and mathematicians made him the appropriate man to serve as the interpreter of Gauss and to subject Fourier series to a penetrating analysis. Dirichlet's beautiful lectures on number theory from 1863 still form one of the best introductions to Gauss's investigations in number theory. It also contains many new results. In a paper of 1840, Dirichlet showed how to apply the full power of the theory of analytical functions to problems in number theory. It was in these investigations that he introduced the Dirichlet series. He also extended the notion of quadratic irrationalities to that of general algebraic domains of rationality. Dirichlet first gave a rigorous convergence proof of Fourier series, and in this way contributed to a correct understanding of the nature of a function. He also introduced into the calculus of variations the so-called Dirichlet principle, which postulated the existence of a function that minimizes a certain integral under given boundary conditions. It was a modification of a principle which Gauss had introduced in his potential theory of 1839-40, and it later served Riemann as a powerful tool in solving problems in potential theory. Hilbert eventually established rigorously the validity of this principle. With Bernhard Riemann, Dirichlet's successor at Göttingen, we reach the man who more than any other has influenced the course of modern mathematics. Riemann was the son of a country minister and studied at the University of Göttingen, where in 1851 he obtained his doctor's degree. In 1854 he became a private docent, and in 1859 a professor at the same university. He was sickly, like Abel, and spent his last days in Italy, where he died in 1866 at 40 years of age. In his short life he published only a relatively small number of papers, but each of them was, and is, important, and several have opened entirely new and productive fields. In 1851 appeared Riemann's doctoral thesis on the theory of complex functions, U for theta, f, x, ie da. Like D'Alembert and Cauchy, Riemann was influenced by hydrodynamical considerations. He mapped the xy plane conformally on the uv plane and established the existence of a function capable of transforming any simply connected region in one plane into any simply connected region in the other plane. This led to the conception of the Riemann surface, which introduced topological considerations into analysis. At that time, topology was still an almost untouched subject on which J.B. Listing had published a paper in the Göttinger-Studien of 1847. Riemann showed its central importance for the theory of complex functions. This thesis also clarified Riemann's definition of a complex function. Its real and imaginary parts have to satisfy the Cauchy-Riemann equations in a given region, and furthermore have to satisfy certain conditions as to boundary and singularities. Riemann applied his ideas to hypergeometric and abelian functions in 1857. Freely using Dirichlet's principle, as he called it. Among his results was the discovery of the genus of a Riemann surface as a topological invariant and as a means of classifying abelian functions. A posthumously published paper applies his ideas to minimal surfaces in 1867. To this branch of Riemann's activity also belong his investigations on elliptical modular functions and theta series in multiple independent variables, as well as those on linear differential equations with algebraic coefficients. Riemann became a private docent in 1850 by submitting no less than 2 fundamental papers. One on trigonometric series and the foundations of analysis, the other on the foundations of geometry. The first of these papers analyzed Dirichlet's conditions for the expansion of a function in a Fourier series. One of these conditions was that the function be integrable. But what does this mean? Cauchy and Dirichlet had already given certain answers. Riemann replaced them with his own, more comprehensive one. He gave that definition which we now know as the Riemann integral, and which was replaced only in the 20th century by the Lebesgue integral. Riemann showed how functions defined by a Fourier series may exhibit such properties as the possession of an infinite number of maxima or minima, which older mathematicians would not have accepted in their definition of a function. The concept of a function began seriously to emancipate from the idea of a curve described by freely leading the hand, as Euler had put it. In his lectures, Riemann gave an example of a continuous function without derivatives. An example of such a function which Weierstrass had given was published in 1875. Mathematicians refused to take such functions very seriously and called them pathological functions. Modern analysis has shown how natural such functions are, and how Riemann here again had penetrated into a fundamental field of mathematics. The other paper of 1854 deals with the hypotheses on which geometry is based. Space was introduced as a topological manifold of an arbitrary number of dimensions. A metric was defined in such a manifold by means of a quadratic differential form, where Riemann, in his analysis, had defined a complex function by its local behavior. In this paper he defined the character of space in the same way. Riemann's unifying principle not only enabled him to classify all existing forms of geometry, including the still very obscure non-Euclidean geometry, but also allowed the creation of any number of new types of space, many of which have since found a useful place in geometry and mathematical physics. Riemann published this paper without any analytical technique, which made his ideas difficult to follow. Later, some of the formulas appeared in a prize essay on the distribution of heat on a solid, which Riemann submitted to the French Academy in 1861. Here we find a sketch of the transformation theory of quadratic forms. The last paper of Riemann which must be mentioned is his discussion of the number of primes less than a given number. From 1859. It was an application of complex number theory to the distribution of primes, and it analyzed Gauss's suggestion that the number of primes approximates the logarithmic integral. This paper is celebrated because it contains the so-called Riemann hypothesis that Euler's zeta function, if considered for complex values, has all non-real zeros on the line with real part equal to 1/2. This hypothesis has never been proved, nor has it been disproved. Riemann's concept of a function of a complex variable has often been compared to that of Weierstrass. Karl Weierstrass was for many years a teacher at Prussian gymnasia, or Latin high schools, and in 1856 became professor of mathematics at the University of Berlin, where he taught for 30 years. His lectures, always meticulously prepared, enjoyed increasing fame. It is mainly through these lectures that Weierstrass ideas have become the common property of mathematicians. In his gymnasial period, Weierstrass wrote several papers on hyperelliptic integrals, abelian functions, and algebraic differential equations. His best-known contribution is his foundation of the theory of complex functions on the power series. This was in a certain sense a return to Lagrange, with the difference that Weierstrass worked in the complex plane and with perfect rigor. The values of the power series inside its circle of convergence represent the function element, which is then extended, if possible, by so-called analytic continuation. Weierstrass especially studied entire functions defined by infinite products. His elliptic function has become as established as the older functions of Jacobi. Weierstrass' fame has been based on his extremely careful reasoning, on Weierstrassian rigor, which is not only apparent in his function theory, but also in his calculus of variations. He clarified the notions of minimum, of function, and of derivative, and with this eliminated the remaining vagueness of expression in the fundamental concepts of the calculus. He was the mathematical conscience par excellence, methodological and logical. Another example of his meticulous reasoning is his discovery of uniform convergence. With Weierstrass began that reduction of the principles of analysis to the simplest arithmetical concepts which we call the arithmetization of mathematics. It is essentially a merit of the scientific activity of Weierstrass that there exists at present in analysis full agreement and certainty concerning the course of such types of reasoning which are based on the concept of irrational number and of limit in general. We owe it to him that there is unanimity on all results in the most complicated questions concerning the theory of differential and integral equations, despite the most daring and diversified combinations with application of super, juxta, and transposition of limits. This arithmetization was typical of the so-called School of Berlin, and especially of Leopold Kronecker. To this school belonged eminent mathematicians, proficient in algebra and the theory of algebraic numbers, such as Kronecker, Kummer, and Frobenius. With these men we may associate Dedekind and Cantor. Ernst Kummer was called to Berlin in 1855 as successor to Dirichlet. He taught there until 1883, when he voluntarily stopped doing mathematical work because he felt the onset of a decline in productivity. Kummer further developed the differential geometry of congruences which Hamilton had outlined, and in the course of his study discovered the quartic surface with 16 nodal points, which is named after him. His reputation is primarily based on his introduction of the ideal numbers in the theory of algebraic domains of rationality in 1846. This theory was inspired partly by Kummer's attempts to prove Fermat's great theorem, and partly by Gauss's theory of biquadratic residues, in which the conception of prime factors had been introduced within the domain of complex numbers. Kummer's ideal factors allowed a unique decomposition of numbers into prime factors in a general domain of rationality. This discovery made possible great advances in the arithmetic of algebraic numbers, which were later masterfully summarized in the report of David Hilbert written for the German Mathematical Society in 1894. The theory of Dedekind and Weber, which established a relation between the theory of algebraic functions and the theory of algebraic numbers in a certain domain of rationality in 1882, was an example of the influence of Kummer's theory on the process of arithmetization of mathematics. Leopold Kronecker. Dazu mussten der Frau Konsequenheit andere Nice were Cézanne Weiss. A man of private means settled in Berlin in 1855, where he taught for many years at the university without a formal professional chair, only accepting one after Kummer's retirement in 1883. Kronecker's main contributions were in elliptic functions, ideal theory, and in the arithmetic of quadratic forms. His published lectures on the theory of numbers are careful expositions of his own and of previous discoveries, and also show clearly his belief in the necessity of the arithmetization of mathematics. This belief was based on his search for rigor. Mathematics, he thought, should be based on number, and all number on the natural number. The number pi, for instance, rather than be derived in the usual geometrical way, should be based on the series 4, 4, 3, 4, 5, 4, 7, and so on, and thus on a combination of integer numbers. Certain continued fractions for pi might also serve the same purpose. Kronecker's endeavor to force everything mathematical into the pattern of number theory is illustrated by his well-known statement at a meeting in Berlin in 1886. The integer numbers have been made by God. Everything else is the work of man. He accepted a definition of a mathematical entity only in the case that it can be verified in a finite number of steps. Thus he coped with the difficulty of the actually infinite by refusing to accept it. Plato's slogan that God always geometrizes was replaced, in Kronecker's school, by the slogan that God always arithmetizes. Kronecker's teaching on the actually infinite was in flagrant contrast to the theories of Dedekind, and especially of Cantor. Richard Dedekind, for 31 years professor at the Technische Hochschule in Brunswick, constructed a rigorous theory of the irrational. In two small books, Continuity and Irrational Numbers from 1872, and The Nature and Meaning of Numbers from 1882, he accomplished for modern mathematics what Eudoxus had done for Greek mathematics. There is a great similarity between the Dedekind cut, with which modern mathematics defines irrational numbers, and the ancient Eudoxus theory, as presented in the fifth book of Euclid's Elements. Cantor and Weierstrass gave arithmetical definitions of the irrational numbers, differing somewhat from the Dedekind theory, but based on similar considerations. The greatest heretic in Kronecker's eyes, however, was Georg Cantor. Cantor, who taught at Halle from 1869 until 1905, is known not only because of his theory of the irrational number, but also because of his theory of sets. With this theory, Cantor created an entirely new field of mathematical research, which was able to satisfy the most subtle demands of rigor once its premises were accepted. Cantor's publications began in 1870 and continued for many years. In 1883, he published his Foundations of a General Theory of Manifolds. In these papers, Cantor developed a theory of transfinite cardinal numbers based on a systematical mathematical treatment of the actually infinite. He assigned the lowest transfinite cardinal number to a denumerable set, giving the continuum a higher transfinite number, and it thus became possible to create an arithmetic of transfinite numbers analogous to ordinary arithmetic. Cantor also defined transfinite ordinal numbers, expressing the way in which infinite sets are ordered. These discoveries of Cantor were a continuation of the ancient scholastic speculations on the nature of the infinite, and Cantor was well aware of it. He defended St. Augustine's full acceptance of the actually infinite, but had to defend himself against the opposition of many mathematicians who refused to accept the infinite except as a process expressed by the symbol for infinity. Cantor's leading opponent was Kronecker, who represented a totally opposite tendency in the same process of arithmetization of mathematics. Cantor finally won full acceptance when the enormous importance of his theory for the foundation of real function theory and of topology became more and more obvious. This especially after Lebesgue in 1901 had enriched the theory of sets with his theory of measure. There remained logical difficulties in the theory of transfinite numbers, and paradoxes appeared, such as those of Burali-Forti and Russell. This again led to different schools of thought on the foundation of mathematics. The 20th century controversy between the formalists and the intuitionists was a continuation on a novel level of the controversy between Cantor and Kronecker. Contemporaneous with this remarkable development of algebra and analysis was the equally remarkable flowering of geometry. It can be traced back to Mung's instruction, in which we find the roots of both the synthetic and the algebraic method in geometry. In the work of Mung's pupils, both methods became separated. The synthetic method developed into projective geometry, and the algebraic method into our modern analytical and algebraic geometry. Projective geometry, as a separate science, began with Poncelet's book of 1822. There were priority difficulties. As so often in cases concerning a fundamental discovery, since Poncelet had to face the rivalry of Joseph Gergonne, professor at Montpellier. Gergonne published several important papers on projective geometry, in which he grasped the meaning of duality in geometry, simultaneously with Poncelet. These papers appeared in the Annals of Pure and Applied Mathematics, the first purely mathematical periodical. Gergonne was its editor. It appeared from 1810 to 1832. Typical of Poncelet's mode of thinking was another principle, that of continuity, which enabled him to derive the properties of one figure from those of another. He expressed the principle as follows. Consider an arbitrary figure in a general position, and in some respects indeterminate among all those positions which it can take without violating the laws. The conditions, the connection existing between the different parts of the system. Suppose that one or more relations or properties, metrical ones, descriptive ones, have been found in accordance with these data. Is it not evident that when conserving these same data, we subject certain parts of the original figure to some continuous movement, that the properties and relations which were found for the first system will be applicable to the successive stages of this system, if only the particular modifications are taken into account? For instance, certain quantities may have vanished or changed their sense or sign. This was a principle which had to be handled with great care since the formulation was far from precise. Only modern algebra has been able to define its domain more accurately. In the hands of Poncelet and his school, it led to interesting, new, and accurate results, especially when it was applied to changes from the real to the imaginary. It thus enabled Poncelet to state that all circles in the plane had, ideally, two imaginary points at infinity in common, which also brought in the so-called line at infinity of the plane. G. H. Hardy has remarked that this meant that projective geometry accepted the actually infinite without any scruples. The analysts were to remain divided on this subject. Poncelet's ideas were further developed by German geometers. In 1826 appeared the first of Steiner's publications. In 1827, Mobius' barycentric calculus. In 1828, the first volume of Plucker's analytical geometry. In 1831 appeared the second volume, followed in 1832 by Steiner's systematic development. The last of the great German pioneer works in this type of geometry appeared in 1847 with the publication of von Stout's axiomatic geometry of position. Both the synthetic and the algebraic approaches to geometry were represented among these German geometers. The typical representative of the synthetic, or pure, school was Jakob Steiner, a self-made Swiss farmer's son, a shepherd boy, who became enamored of geometry by making the acquaintance of Pestalozzi's ideas. He decided to study at Heidelberg, and later taught at Berlin, where from 1834 until his death in 1863 he held a chair at the university. Steiner was thoroughly a geometer. He hated the use of algebra and analysis to such an extent that he even disliked figures. Geometry, in his opinion, could best be learned by concentrated thought. Calculating, he said, replaces while geometry stimulates thinking. This was certainly true for Steiner himself, whose methods have enriched geometry with a large number of beautiful and often intricate theorems. We owe him the discovery of the Steiner surface with a double infinity of conics on it, also called the Roman surface. He often omitted the proof of his theorems, which has made Steiner's collected works a treasure trove for geometers in search of problems to solve. Steiner constructed his projective geometry in a strictly systematic way, passing from perspectivity to projectivity, and from there to the conic sections. He also solved a number of isoperimetrical problems in his own typical geometrical way. His proof in 1836 that the circle is the figure of largest area for all closed curves of given perimeter made use of a procedure by which every figure of given perimeter, which is not a circle, could be changed into another one of the same perimeter and of larger area. Steiner's conclusion that the circle, therefore, represented the maximum suffered from one omission, he did not prove the actual existence of a maximum. Dirichlet tried to point it out to Steiner. A rigorous proof was later given by Weierstrass. Steiner still needed a metric to define the cross ratio of 4 points or lines. This defect in the theory was removed by Christian von Stout, for many years a professor at the University of Erlangen. In his geometry of position, defined the anharmonic ratio of 4 points on a straight line in a purely projective way, and then showed its identity with the cross ratio. He used for this purpose the so-called Möbius net construction, which leads to axiomatic considerations closely related to Dedekind's work when irrational values of projective coordinates are introduced. In 1857, von Staudt showed how imaginary elements can be rigorously introduced into geometry as double elements of elliptic involutions. During the next decades, synthetic geometry grew greatly in content on the foundations laid by Poncelet, Steiner, and von Staudt. It was eventually made the subject of a number of standard textbooks, of which Reyes' Geometry of Position from 1868, 3rd edition 1886-92, is one of the best-known examples. Representatives of algebraic geometry were Möbius and Plucker in Germany, Chasles in France, and Cayley in England. August Ferdinand Möbius Dortar. For more than 50 years an observer, and later director of the Leipzig Astronomical Observatory, was a scientist of many parts. In his book, Barycentric Calculus, he was the first to introduce homogeneous coordinates. When the masses are placed at the vertices of a fixed triangle, Möbius gave to the center of gravity, or barycenter, of these masses the coordinates of those masses, and showed how these coordinates are well fitted to describe the projective and affine properties of the plane. Homogeneous coordinates, from this time on, became the accepted tool for the algebraic treatment of projective geometry. Working in quiet isolation, not unlike his contemporary von Staudt, Möbius made many other interesting discoveries. An example is the null system in the theory of line congruences, which he introduced in his textbook on statics in 1837. The Möbius strip, a first example of a non-orientable surface, is a reminder of the fact that Möbius is also one of the founders of our modern science of topology. Julius Plucker, who taught for many years at Bonn, was an experimental physicist as well as a geometer. He made a series of discoveries in crystal magnetism, electrical conduction in gases, and spectroscopy, in a series of papers and books. Especially in his new Geometry of Space from 1868-69, he reconstructed analytical geometry by the application of a wealth of new ideas. Plucker showed the power of the abbreviated notation, in which, for instance, the equation cone (8 represents a pencil of conics. In this book, he introduced homogeneous coordinates known as projective coordinates based on a fundamental tetrahedron, and also the fundamental principle that geometry need not solely be based on points as basic elements. Lines, planes, circles, spheres can all be used as the elements on which a geometry can be based. This fertile conception threw new light on both synthetic and algebraic geometry and created new forms of duality. The number of dimensions of a particular form of geometry could now be any positive integer number, depending on the number of parameters necessary to define the element. Plucker also published a general theory of algebraic curves in the plane, in which he derived the Plucker relations between the number of singularities in 1834 and 1839. Michel Chasles. For many years, the leading representative of geometry in France, was a pupil of the École Polytechnique in the later days of Monge, and in 1841 became professor at this institute. In 1846, he accepted the chair of higher geometry, especially established for him at the Sorbonne, where he taught for many years. Chasles' work had much in common with that of Plucker, notably in his ability to obtain the maximum of geometrical information from his equations. It led him to adroit operation with isotropic lines and circular points at infinity. Chasles followed Poncelet in the use of enumerative methods, which in his hands developed into a new branch of geometry, the so-called enumerative geometry. This field was later fully explored by Hermann Schubert in his Calculus of Enumerative Geometry from 1879, and by H.G. Zeuthen in his Enumerative Methods from 1914. Both books reveal the strength as well as the weakness of this type of algebra in geometrical language. Its initial success provoked a reaction led by E. who stressed that precision in geometricists may not perpetually be treated as incidental. Chasles had a fine appreciation for the history of mathematics, especially of geometry. His well-known historical survey on the origin and development of methods in geometry from 1837 stands at the beginning of the modern history of mathematics. It is a very readable text on Greek and modern geometry, and is also a good example of a history of mathematics written by a productive scientist. During these years of almost feverish productivity in the new projective and algebraic geometries, another novel, and even more revolutionary type of geometry lay hidden in a few obscure publications discarded by most leading mathematicians. The question of whether Euclid's parallel postulate is an independent axiom or can be derived from other axioms had puzzled mathematicians for 2,000 years. Ptolemy had tried to find an answer in antiquity, Nasir al-Din in the Middle Ages, and Lambert and Legendre in the 18th century. All these men had tried to prove the axiom and had failed, even if they reached some very interesting results in the course of their investigations. Gauss was the first man who believed in the independent nature of the parallel postulate, which implied that other geometries based on another choice of axiom were logically possible. Gauss never published his thoughts on this subject. The first to challenge openly the authority of 2 millennia and to construct a non-Euclidean geometry were a Russian, Nikolai Ivanovich Lobachevsky, and a Hungarian, János Bolyai. The first to publish his idea was Lobachevsky, who was a professor in Kazan and lectured on the subject of Euclid's parallel axiom in 1826. His first book appeared in 1829-30 and was written in Russian. Few people took notice of it. Even a later, German edition, with the title Geometric Researches on the Theory of Parallels, received little attention, even though Gauss showed interest. By that time, Bolyai had already published his ideas on the subject. János Johann Bolyai was the son of a mathematics teacher in a provincial town of Hungary. This teacher, Farkas Wolfgang Bolyai, had studied at Göttingen when Gauss was also a student there. Both men kept up an occasional correspondence. Farkas spent much time trying to prove Euclid's fifth postulate, but could not come to a definite conclusion. His son inherited his passion, and also began to work on a proof despite his father's plea to do something else. You should detest it just as much as lewd intercourse. It can deprive you of all your leisure, your health, your rest, and the whole happiness of your life. This abysmal darkness might perhaps devour 1,000 towering Newtons. It will never be light on earth. János Bolyai entered the army and built up a reputation as a dashing officer. He began to accept Euclid's postulate as an independent axiom and discovered that it was possible to construct a geometry based on another axiom in which through one point in a plane an infinity of lines can be laid which do not intersect a line in the plane. This was the same idea which had already occurred to Gauss and Lobachevsky. Bolyai wrote down his reflections, which were published in 1832 as an appendix to a book by his father, and which had the title Appendix Scientiam Spati, Absolute Verum Exhibens. The worrying father wrote to Gauss for advice on the unorthodox views of his son. When the answer from Göttingen came, it contained enthusiastic approval of the younger Bolyai's work. Added to this was Gauss's remark that he could not praise Bolyai, since this would mean self-praise, the ideas of the appendix having been his own for many years. Young János was deeply disappointed by this letter of approval, which elevated him to the rank of a great scientist, but robbed him of his priority. His disappointment increased when he met with little further recognition. He became even more upset when Lobachevsky's book was published in German in 1840. He never published any more mathematics. Bolyai's and Lobachevsky's theories were similar in principle, though their papers were very different. It is remarkable how the new idea sprang up independently in Göttingen, Budapest, and Kazan, and in the same period, after an incubation period of 2,000 years. It is also remarkable how they matured partly outside the geographical periphery of the world of mathematical research. Sometimes great new ideas are born outside, not inside, the schools. Non-Euclidean geometry, the name is due to Gauss, remained for several decades an obscure field of mathematics. Most mathematicians ignored it, the prevailing Kantian philosophy refusing to take it seriously. The first leading scientist to understand its full importance was Riemann, whose general theory of manifolds in 1854 made full allowance not only for the existing types of non-Euclidean geometry, but also for many other so-called Riemannian geometries. However, full acceptance of these theories came only when the generation after Riemann began to understand the meaning of his theories 1870 and later. Still another generalization of classical geometry originated in the years before Riemann, and did not find full appreciation until after his death. This was the geometry of more than 3 dimensions. It came fully developed into the world in Grassmann's theory of extension of 1844. Hermann Grassmann was a teacher at the gymnasium in Stettin, and was a man of extraordinary versatility. He wrote on such varied subjects as electric currents, colors and acoustics, linguistics, botany and folklore. His Sanskrit dictionary on the Rigveda is still in use. The Theory of Extension, of which a revised and more readable edition was published in 1861, was written in strictly Euclidean form. It built up a geometry in a space of n dimensions, first in affine then in metrical space. Grassmann used an invariant symbolism, in which we now recognize a vector and tensor notation. His gap products are tensors, but which made his work almost inaccessible to his contemporaries. A later generation took parts of Grassmann's structure to build up vector analysis for affine and for metrical spaces. Although Cayley in 1843 introduced the same concept of a space of n dimensions, in a far less forbidding form, geometry of more than 3 dimensions was received with distrust and incredulity. Here again Riemann's address of 1854 made full appreciation easier. Added to Riemann's ideas were those of Plucker, who pointed out that space elements need not be points, 1865, so that the geometry of lines in 3 space could be considered as a 4-dimensional geometry, or as Klein has stressed, as the geometry of a 4-dimensional quadric in a 5-dimensional space. Full acceptance of geometries of more than 3 dimensions occurred only in the latter part of the 19th century, mainly because of their use in interpreting the theory of algebraic and differential forms in more than 3 variables. The names of Hamilton and Cayley show that by 1840, English-speaking mathematicians had at last begun to catch up with their continental colleagues. Until well into the 19th century, the Cambridge and Oxford dons regarded any attempt at improvement of the theory of fluxions as an impious revolt against the sacred memory of Newton. The result was that the Newtonian school of England and the Leibnizian school of the continent drifted apart to such an extent that Euler, in his integral calculus of 1768, considered a union of both methods of expressions as useless. The dilemma was broken in 1812 by a group of young mathematicians at Cambridge who, under the inspiration of the older Robert Woodhouse, formed an analytical society to propagate the differential notation. Leaders were George Peacock, Charles Babbage, and John Herschel. They tried, in Babbage's words, to advocate the principles of pure deism as opposed to the dot age of the university. This movement met initially with severe criticism, which was overcome by such actions as the publication, in 1816, of an English translation of Lacroix's elementary treatise on differential and integral calculus, 2nd edition, 1806. The new generation in England now began to participate in modern mathematics. The first important contribution came not from the Cambridge group, however, but from some mathematicians who had taken up continental mathematics independently. The most important of these mathematicians were Hamilton and George Green. It is interesting to notice that with both men, as well as with Nathaniel Bowditch in New England, the inspiration to study pure deism came from the study of Laplace's celestial mechanics. Green, who was a self-taught miller's son of Nottingham, followed with great care the new discoveries in electricity. There was, at that time, around 1825, almost no mathematical theory to account for the electrical phenomena. Poisson in 1812 had made no more than a beginning. Green read Laplace, and, in his own words, considering how desirable it was that a power of universal agency, like electricity, should, as far as possible, be submitted to calculation, and reflecting on the advantages that arise in the solution of many difficult problems, from dispersing altogether with a particular examination of each of the forces which actuate the various bodies in any system, by confining the attention solely on that peculiar function on whose differentials they all depend, I was induced to try whether it would be possible to discover any general relations existing between this function and the quantities of electricity in the bodies producing it. The result was Green's essay on the application of mathematical analysis to theories of electricity, and Magnetism, 1828, the first attempt at a mathematical theory of electromagnetism. It was the beginning of modern mathematical physics in England, and with Gauss' paper of 1839, established the theory of potential as an independent branch of mathematics. Gauss did not know Green's paper, which only became more widely known when William Thomson, the later Lord Kelvin, had it reprinted in Crell's Journal of 1846. Yet the kinship of Gauss and Green was so close that where Green selected the term potential function, Gauss selected almost the same term, potential, for the solution of Laplace's equation. Two closely related identities. Connecting line and surface integrals are called the formula of Green and the formula of Gauss. The term Green's function in the solution of partial differential equations also honors the miller's son who studied Laplace in his spare time. We have no room for a sketch of the further development of mathematical physics in England, or for that matter, in Germany. With this development, the names of Stokes, Rayleigh, Kelvin, and Maxwell, of Kirchhoff and Helmholtz, of Gibbs and of many others are connected. These men contributed to the solution of partial differential equations to such an extent that mathematical physics and the theory of linear partial differential equations of the second order sometimes seem to become identified. Mathematical physics, however, brought fertile ideas to other fields of mathematics, to probability and complex function theory, as well as to geometry. Of particular importance was James Clerk Maxwell's treatise on electricity and magnetism, 2 volumes. 1873, which gave a systematic mathematical exposition of the theory of electromagnetism based on Faraday's experiments. This theory of Maxwell eventually dominated mathematical electricity, and later inspired the theories of Lorentz on the electron and Einstein on relativity. 19th century pure mathematics in England was primarily focused on algebra, with significant applications to geometry, and 3 men, Cayley, Sylvester, and Salmon, were leading figures in this field. Arthur Cayley devoted his early years to studying and practicing law, but in 1863 he accepted the new Sadolarian Professorship of Mathematics at Cambridge, where he taught for 30 years. In the 1840s, while practicing law in London, Cayley met Sylvester, who was an actuary at that time. This meeting marked the beginning of their common interest in the algebra of forms, or quantics, as Cayley called them. Their collaboration led to the foundation of the theory of algebraic invariance. This theory had been developing for many years, especially after determinants began to be studied. The early work of Cayley and Sylvester went beyond mere determinants. It was a conscious effort to create a systematic theory of invariance of algebraic forms, complete with its own symbolism and rules of composition. This theory was later refined by Aronhold and Clebsch in Germany, and became the algebraic counterpart of Poncelet's projective geometry. Cayley's extensive work covered a wide range of topics, including finite groups, algebraic curves, determinants, and invariance of algebraic forms. Among his most notable works are his 9 memoirs on quantics, 1854-78. The 6th paper in this series, 1859, introduced the projective definition of a metric concerning a conic section. This discovery led Cayley to define the Euclidean metric projectively, thereby positioning metrical geometry within the framework of projective geometry. The connection of this projective metric to non-Euclidean geometry was later identified by Felix Klein. James Joseph Sylvester was not only a mathematician, but also a poet and wit, and alongside Leibniz, he was one of the greatest creators of new terms in the history of mathematics. From 1855 to 1869, he taught at Woolwich Military Academy. He was twice in America, first as a professor at the University of Virginia, 1841-42, and later at Johns Hopkins University in Baltimore, 1877-83. During his second stint in America, he helped establish graduate work in mathematics at American universities. Sylvester's teaching contributed to the flourishing of mathematics in the United States. 2 of Sylvester's many contributions to algebra have become classics: his theory of elementary divisors, 1851, rediscovered by Weierstrass in 1868, and his law of inertia of quadratic forms, 1852, already known to Jacobi and Riemann but not published. We also owe to Sylvester many terms now generally accepted, such as invariant, covariant, contravariant, cogradient, and syzygy. Many anecdotes have been attributed to him, several of the absent-minded Professor Variety. The third prominent English algebraist geometer was George Salmon Dodot, who was connected with Trinity College, Dublin, Hamilton's alma mater, where he instructed in both mathematics and divinity. His main contribution lies in his well-known textbooks, which excel in clarity and charm. These books introduced several generations of students to analytical geometry and invariant theory, and are still highly regarded. They include Conic Sections, 1848, Topsy, Higher Plane Curves, 1852, Modern Higher Algebra, 1859, and the Analytic Geometry of Three Dimensions, 1862. Two significant products of the algebra of the United Kingdom deserve special attention: Hamilton's quaternions and Clifford's biquaternions. Hamilton, the Royal Astronomer of Ireland, having completed his work on mechanics and optics, turned to algebra in 1835. His theory of algebraic couples, 1835, defined algebra as the science of pure time, and constructed a rigorous algebra of complex numbers, based on the concept of a complex number as a number pair. This was likely independent of Gauss, who in his theory of biquadratic residues, 1831, also constructed a rigorous algebra of complex numbers based on the geometry of the complex plane. Both conceptions are now equally accepted. Hamilton subsequently tried to explore the algebra of number triples, number quadruples, and so on. The breakthrough came in October 1843, when, while walking under a Dublin bridge, he discovered the quaternion. His investigations on quaternions were published in two significant works: Lectures on Quaternions, 1853, and The Posthumous Elements of Quaternions, 1866. The most well-known part of this quaternion calculus is the theory of vectors, a term coined by Hamilton, which is also part of Grassmann's theory of extension. In Hamilton's time, and long afterward, quaternions themselves were the subject of exaggerated admiration. Some British mathematicians saw the calculus of quaternions as a kind of Leibnizian Arithmetica Universalis, which of course aroused a reaction, Heaviside versus Tate, in which quaternions lost much of their glory. The theory of hypercomplex numbers, elaborated by Peirce, Study, Frobenius, and Cartan, eventually placed quaternions in their legitimate place as the simplest associative number system of more than 2 units. The enthusiasm for quaternions even led to the formation of the International Association for Promoting the Study of Quaternions and Allied Systems of Mathematics, which disappeared as a casualty of World War I. Another aspect of the quaternion controversy was the debate between supporters of Hamilton and Grassmann, when vector analysis emerged as an independent branch of mathematics through the efforts of Gibbs in America and Heaviside in England. This controversy raged between 1890 and World War I, and was finally resolved by the application of group theory, which established the merits of each method in its respective field. William Kingdon Clifford, who died in 1879 at the age of 33, taught at Trinity College, Cambridge, and at University College, London. He was one of the first Englishmen to understand Riemann, and shared with him a deep interest in the origin of our space conceptions. Clifford developed a geometry of motion, for which he generalized Hamilton's quaternions into biquaternions, 1873–76. These were quaternions with coefficients taken from a system of complex numbers, a UB, where e squared may be +1, -1, or 0, and could also be used for studying motion in non-Euclidean spaces. Clifford's common sense of the exact sciences is still good reading, and illustrates his intellectual kinship with Felix Klein. This kinship is also evident in the term spaces of Clifford-Klein for certain closed Euclidean manifolds in non-Euclidean geometry. If Clifford had lived longer, Riemann's ideas might have influenced British mathematicians a generation earlier than they actually did. For many decades, pure mathematics in the English-speaking countries maintained a strong emphasis on formal algebra. This influenced the work of Benjamin Peirce of Harvard University, a pupil of Nathaniel Bowditch, who did distinguished work in celestial mechanics and published his linear associative algebras in 1870, one of the first systematic studies of hypercomplex numbers. The formalist trend in English mathematics may also account for the investigation of the laws of thought, 1854, by George Boole of Queen's College, Dublin. Boole showed how the laws of formal logic, codified by Aristotle and taught for centuries in universities, could be made the subject of a calculus. This established principles in harmony with Leibniz's idea of a characteristica generalis. This algebra of logic opened a school of thought that aimed to unify logic and mathematics. This movement received further impetus from Gottlob Frege's book Die Grundlagen der Arithmetik 1884, which derived arithmetical concepts from logic. These investigations culminated in the 20th century with the Principia Mathematica of Bertrand Russell and Alfred North Whitehead, 1910-13, and influenced the later work of Hilbert on the foundations of arithmetic and the elimination of the paradoxes of the infinite. The papers on the theory of invariance by Cayley and Sylvester received great attention in Germany, where several mathematicians developed the theory into a science based on a complete algorithm. The main figures were Hess, Aronhold, Clebsch, and Gordon. Hesse, a professor at Königsberg, and later at Heidelberg and Munich, demonstrated the power of abbreviated methods in analytical geometry. He preferred reasoning with homogeneous coordinates and determinants. Aronhold, who taught at the Technische Hochschule in Berlin, developed a consistent symbolism in invariant theory with the aid of so-called ideal factors in 1858. This symbolism was further refined by Clebsch in 1861, becoming the almost universally accepted method for investigating algebraic invariance systematically. We now recognize in this symbolism, as well as in Hamilton's vectors, Grassmann's gap products, and Gibbs' dyadics, special aspects of tensor algebra. This theory of invariance was later enriched by Paul Gordon of the University of Erlangen, who proved, 1868-69, that to every binary form belongs a finite system of rational invariance and covariance, in which all other rational invariance and covariance can be expressed in rational form. This theorem of Gordon, the Endlichkeitssatz, was extended by Hilbert in 1890 to algebraic forms in n variables. Alfred Clebsch, professor at Karlsruhe, Gießen, and Göttingen, made remarkable achievements during his short life. He published a book on elasticity, 1862, and applied his theory of invariance to projective geometry. He was one of the first to understand Riemann, and was a founder of the branch of algebraic geometry that applied Riemann's theory of functions and multiply connected surfaces to real algebraic curves. Clebsch-Gordon's theory der abelschen Funktionen, 1866, outlined these ideas. Clebsch also founded the Mathematische Annalen, a leading mathematical journal for more than 60 years. His lectures on geometry, published by F. Lindemann.il, remain a standard text on projective geometry. Baum. By 1870, mathematics had grown into a vast and complex structure, divided into many specialized fields. Even great mathematicians like Hermite, Weierstrass, Cayley, and Beltrami could only master a few of these fields. Specialization continued to grow, leading to a reaction against it. Some of the most significant achievements of the last 100 years have resulted from synthesizing different areas of mathematics. Such a synthesis was realized in the 18th century by Lagrange and Laplace in their works on mechanics. Their work remained a basis for powerful research of varied character. The 19th century added new unifying principles, notably the theory of groups and Riemann's conceptions of function and space. These principles can best be understood through the work of Klein, Lie, and Poincaré. Felix Klein was Plicker's assistant in Bonn during the late 60s, where he learned geometry. He visited Paris in 1870, where he met Sophus Lie, a Norwegian 6 years his senior, who had only recently become interested in mathematics. The two young men met French mathematicians, including Camille Jordan of the École Polytechnique, and studied their work. Jordan had just written the Traité de Substitutions, a book on substitution groups and Galilei theory of equations. Klein and Lie began to understand the central importance of group theory, and subsequently divided the field of mathematics more or less into two parts. Klein focused on discontinuous groups, while Lie concentrated on continuous groups. In 1872, Klein became a professor at Erlangen. In his inaugural address, he explained the importance of the group concept for classifying different fields of mathematics. This address, known as the Erlangen Program, declared that every geometry is the theory of invariance of a particular transformation group. By extending or narrowing the group, one can transition from one type of geometry to another. Euclidean geometry studies the invariance of the metrical group, while projective geometry studies the invariance of the projective group. Classifying groups of transformation provides a classification of geometry, and the theory of algebraic and differential invariance of each group gives the analytical structure of a geometry. Cayley's projective definition of a metric allows us to consider metrical geometry within the frame of projective geometry. Adjunction of an invariant conic to a projective geometry in the plane gives us the non-Euclidean geometries. Even relatively unknown topology received its proper place as the theory of invariance of continuous point transformations. In the previous year, Klein had given an important example of his thinking when he showed how non-Euclidean geometries could be conceived as projective geometries with a Cayley metric. This brought full recognition to the neglected theories of Bolyai and Lobachevsky. Their logical consistency was now established. If there were logical mistakes in non-Euclidean geometry, they could be detected in projective geometry, although few mathematicians were willing to admit such a heresy. Later, this idea of an image of one field of mathematics on another field was often used and played an important role in Hilbert's axiomatics of geometry. The theory of groups allowed for a synthesis of the geometrical and algebraic work of Monge, Poncelet, Gauss, Cayley, Klebsch, Grassmann, and Riemann. Riemann's theory of space, which had offered so many suggestions embodied in the Erlangen program, inspired not only Klein, but also Helmholtz and Lie. Helmholtz studied Riemann's concept of space, partly by looking for a geometrical image of his theory of colors, and partly by investigating the origin of our ocular measure. This led him to explore the nature of geometrical axioms, particularly Riemann's quadratic measurement. Lie improved on Helmholtz's speculations by analyzing the nature of the underlying groups of transformations. This Lie-Helmholtz space problem has been significant not only for relativity and group theory, but also for physiology. Klein gave an exposition of Riemann's concept of complex functions in his booklet on Riemann's theory of algebraic functions and their integrals, 1882, stressing the influence of physical considerations on even the subtlest types of mathematics. In lectures on the icosahedron, 1884, he showed that modern algebra could reveal many new and surprising insights about the ancient Platonic solids. This work studied the rotation groups of the regular solids and their relation to Galois groups of algebraic equations. Klein applied the group concept to linear differential equations, elliptic modular functions, abelian functions, and the new automorphic functions in an interesting and friendly competition with Poincare.I. Under Klein's inspiring leadership, Göttingen, with its traditions of Gauss, Dirichlet, and Riemann, became a world center of mathematical research, attracting young scholars from many nations. Klein's lectures, often circulated in mimeographed form, provided generations of mathematicians with specialized information and an understanding of the unity of their science. After Klein's death in 1925, several of these lecture notes were published in book form. While in Paris, Sophus Lie discovered the contact transformation, key to Hamiltonian dynamics, as part of group theory. After returning to Norway, he became a professor in Christiania and later taught in Leipzig from 1886 to 1898. He devoted his life to the systematic study of continuous transformation groups and their invariants, demonstrating their central importance as a classifying principle in geometry, mechanics, and differential equations. Lie's work was codified in standard tomes edited with the aid of his pupils, Scheffers and Engel. Theorie der Transformationsgruppen, 1888-93. Differentialgleichungen, 1891. Kontinuierliche Gruppen, 1893. Berührungstransformation, 1896. Lie's work has been significantly enriched by the French mathematician Élie Cartan. France, faced with the enormous growth of mathematics in Germany, continued to produce excellent mathematicians in all fields. It is interesting to compare German and French mathematicians: Hermite with Weierstrass, Darboux with Klein, Hadamard with Hilbert, and Paul Tannery with Moritz Cantor. From the 1840s to the 1860s. The leading mathematician in France was Joseph Liouville, a professor at the Collège de France in Paris. Liouville was a good teacher, organizer and editor of the Journal de Mathématiques Pures et Appliquées, He systematically investigated the arithmetic theory of quadratic forms of two and more variables. Liouville's theorem in statistical mechanics shows him as a productive worker in an entirely different field. He established the existence of transcendental numbers, and in 1844 proved that neither e nor e squared could be a root of a quadratic equation with rational coefficients. This was a step in the chain of arguments leading from Lambert's proof in 1761 that pi is irrational to Hermite's proof that e is transcendental, 1873, and to the final proof by F. E. Lindemann, a Weierstrass pupil, that pi is transcendental, 1882. Liouville and several of his associates developed the differential geometry of curves and surfaces. The formulas of Frenet-Serret, 1847, came out of Liouville's circle. Charles Hermite d'Otto, a professor at the Sorbonne and the École Polytechnique, became the leading representative of analysis in France after Cauchy's death in 1857. Hermite's work, like that of Liouville, was in the tradition of Gauss and Jacobi, and also showed kinship with that of Riemann and Weierstrass. Elliptic functions, modular functions, theta functions, number theory, and invariant theory all received his attention, as evidenced by the terms Hermitian numbers and Hermitian forms. His friendship with the Dutch mathematician Stieltjes, who, through Hermite's intervention, obtained a chair at Toulouse, was a great encouragement to the discoverer of the Stieltjes integral and the application of continued fractions to the theory of moments. The appreciation was mutual. You are always right. And I am always wrong, Hermite once wrote to his friend. The 4-volume correspondence 1905 between Hermite and Stieltjes contains a wealth of material, mainly on functions of a complex variable. The French geometrical tradition was gloriously continued in the books and papers of Gaston Darboux. Darboux was a geometer in the sense of Monge, approaching geometrical problems with full mastery of groups and differential equations and working on problems of mechanics with a lively spatial intuition. Darboux was a professor at the Collège de France and was active in teaching for half a century. His most influential work was his standard lectures on the general theory of surfaces, 4 volumes. 1887-96, which presented the results of a century of research in the differential geometry of curves and surfaces. In Darboux's hands, this differential geometry became connected in various ways, with ordinary and partial differential equations, as well as with mechanics. Darboux, with his administrative and pedagogical skills, his fine geometrical intuition, his mastery of analytical technique, and his understanding of Riemann, occupied a position in France somewhat analogous to Klein's in Germany. This second part of the 19th century was the period of the great French comprehensive textbooks on analysis and its applications, often appearing under the name of Cours d'analyse and written by leading mathematicians. The most famous are the Cours d'analyse of Camille Jordan, 3 volumes, 1882-87, and the Traité d'analyse of Émile Picard, 3 volumes, 1891-96, to which was added the Cours d'analyse mathématique by Édouard Goursat, 2 volumes, 1902-5. The greatest French mathematician of the second half of the 19th century was Henri Poincaré, who, from 1881 until his death in 1912, was a professor at the Sorbonne in Paris. No mathematician of his period commanded such a wide range of subjects and enriched them all. Each year he lectured on a different subject. These lectures were edited by students and covered an enormous field: potential theory, light, electricity, conduction of heat, capillarity, electromagnetics, hydrodynamics, celestial mechanics, thermodynamics, probability. Every one of these lectures was brilliant in its own way. Together, they present ideas that have borne fruit in the works of others, while many still await further elaboration. Poincaré also wrote several popular and semi-popular works to give a general understanding of modern mathematical problems. Among these are The Value of Science, 1905, and Science and Hypothesis, 1906. Apart from these lectures, Poincaré published many papers on automorphic and Fouchian functions, differential equations, topology, and the foundations of mathematics, treating with great mastery of technique and full understanding all pertinent fields of pure and applied mathematics. No mathematician of the 19th century, except perhaps Riemann, has so much to say to the present generation. The key to understanding Poincaré's work may lie in his meditations on celestial mechanics, particularly the three-body problem, New Methods of Celestial Mechanics, 3 volumes, 1893. Here, he showed direct kinship with Laplace and demonstrated that even at the end of the 19th century, the ancient mechanical problems concerning the universe had not lost their pertinence to the productive mathematician. It was in connection with these problems that Poincaré studied divergent series and developed his theory of asymptotic expansions, worked on integral invariance, the stability of orbits, and the shape of celestial bodies. His fundamental discoveries on the local behavior of integral curves of differential equations near singularities, as well as their behavior in the large, are related to his work on celestial mechanics. This is also true of his investigations on the nature of probability, another field in which he shared Laplace's interest. Poincaré was like Euler and Gauss. Wherever we approach him, we discover the stimulation of originality. Modern theories concerning relativity, cosmogony, probability, and topology are all vitally influenced by Poincaré's work. The Risorgimento. The national rebirth of Italy also meant the rebirth of Italian mathematics. Several founders of modern mathematics in Italy participated in the struggles that liberated their country from Austria and unified it. Later, they combined political positions with their professional chairs. The influence of Riemann was strong, and through Klein, Clebsch, and Cayley, Italian mathematicians gained knowledge of geometry and the theory of invariance. They also became interested in the theory of elasticity, which has a strong geometrical appeal. Among the founders of the new Italian school of mathematicians were Brioschi, Cremona, and Betti. In 1852, Francesco Brioschi became a professor in Pavia, and in 1862 organized the Technical Institute in Milan, where he taught until his death in 1897. He founded the Annali di Matematica Pura et Applicata, 1858, modeled after Crell's and Liouville's journals. In 1858, Brioschi, Betti, and Casarati visited the leading mathematicians of France and Germany. Volterra later claimed that the scientific existence of Italy as a nation dated from this journey. Brioschi represented the Cayley-Clebsch type of research in algebraic invariance in Italy. Luigi Cremona, after 1873 director of the engineering school in Rome, is known for the birational transformation of plane and space, the Cremona transformations, 1863-65. He was also one of the originators of graphical statics. Eugenio Beltrami, a pupil of Brioschi, held chairs in Bologna, Pisa, Pavia, and Rome. His main work in geometry was done between 1860 and 1870, when his differential parameters introduced a calculus of differential invariance into surface theory. Another contribution of that period was his study of pseudospherical surfaces, which are surfaces with a negative constant Gaussian curvature. On such a pseudosphere, one can realize a two-dimensional non-Euclidean geometry of Bolyai. This, along with Klein's projective interpretation, was a method to show that there were no internal contradictions in non-Euclidean geometry, since such contradictions would also appear in ordinary surface theory. By 1870, Riemann's ideas became more widely understood among the younger generation of mathematicians. His theory of quadratic differential forms was the subject of 2 papers by the German mathematicians E.B. Christoffel and R. Lipschitz, 1870. The first paper introduced the Christoffel symbols. These investigations, combined with Beltrami's theory of differential parameters, led Gregorio Ricci Curbastro in Padua to develop his absolute differential calculus, 1884. This new invariant symbolism was originally constructed for the transformation theory of partial differential equations, but also provided a symbolism suitable for the transformation theory of quadratic differential forms. In the hands of Ricci and some of his pupils, notably Tullio Levi-Civita, the absolute differential calculus developed into what we now call the theory of tensors. Tensors provided a unification of many invariant symbolisms and showed their power in general theorems in elasticity, hydrodynamics, and relativity. The name tensor originates from elasticity. W.A. Voigt taught, 1900. The most brilliant representative of differential geometry in Italy was Luigi Bianchi. His Lessons on Differential Geometry, 2nd ed. 3 volumes, 19029, ranks with Darboux's theory of surfaces as a classical exposition of 19th century differential geometry. David Hilbert, a professor at Göttingen, presented a series of 23 research projects to the International Congress of Mathematicians in Paris in 1900. At that time, Hilbert was already recognized for his work on algebraic forms and had prepared his now famous book on the foundations of geometry, Grundlagen der Geometrie, 1900. This book was inspired by the pioneering work of Moritz Pasch of Gießen, particularly his book Lectures on Modern Geometry, 1882, in which Pasch extended the axiomatic approach to the foundations of geometry. Hilbert's book analyzed the axioms on which Euclidean geometry is based and explained how modern axiomatic research has improved on the achievements of the Greeks. In his 1900 address, Hilbert tried to capture the trend of mathematical research over the past decades and sketch the outline of future productive work. A summary of his projects provides a better understanding of 19th century mathematics. Hilbert first proposed the arithmetical formulation of the concept of the continuum, as presented in the works of Cauchy, Bolzano, and Cantor. He asked whether there is a cardinal number between that of a denumerable set and that of a continuum, and whether the continuum can be considered a well-ordered assemblage. Additionally, he inquired about the compatibility of arithmetical axioms. The next projects addressed the foundations of geometry. Lie's concept of a continuous group of transformations, questioning the necessity of differentiability, and the mathematical treatment of the axioms of physics. Hilbert then posed specific problems in arithmetic and algebra. These included the irrationality or transcendence of certain numbers, such as a raised to the power of e for an algebraic A, and irrational beta, proving Riemann's hypothesis concerning the roots of the zeta function, and formulating the most general law of reciprocity in number theory. He also proposed proving the finiteness of certain complete systems of functions, suggested by the theory of invariance. The 15th question called for a rigorous formulation of Schubert's enumerative calculus, while the 16th focused on the topology of algebraic curves and surfaces. Another problem involved the division of space by congruent polyhedra. The remaining projects dealt with differential equations and the calculus of variations. Hilbert asked whether the solutions of regular problems in the calculus of variations are always analytic, and whether every regular variational problem under given boundary conditions has a solution. He also inquired about the uniformization of analytic relations by means of automorphic functions, and concluded his enumeration with an appeal for further development of the calculus of variations. Hilbert's program demonstrated the vitality of mathematics at the end of the 19th century, in sharp contrast to the pessimistic outlook prevalent toward the end of the 18th century. While some of Hilbert's problems have been solved, others still await their final resolution. The development of mathematics in the years after 1900 has not disappointed the expectations raised at the close of the 19th century. Even Hilbert's genius, however, could not foresee some of the striking developments that have taken place and are still occurring today. 20th century mathematics has followed its own novel path to glory.